RAF night landing, the beam approach, Fido, and the human cost. It is night, and across Britain the countryside is almost completely invisible under strict wartime blackout conditions. England is dark, silent, and waiting. Cloud hangs low over the airfields, trapping moisture and reducing visibility. Fog clings stubbornly to the ground, swallowing lights and landmarks alike. A bomber returns from occupied Europe after a long and dangerous mission. Fuel gauges are close to empty, and engines are no longer running smoothly. The crew has been awake for more than 10 hours, operating under constant stress. They survived anti-aircraft fire, they survived enemy fighters, and they survived the long flight home across hostile skies. Now comes the final challenge. They must land. For the Royal Air Force during the Second World War, landing at night was often the most dangerous phase of the entire mission. In this video we explore how the RAF learned to land aircraft in darkness and poor weather. We'll try and explain how radio beams replaced unreliable human eyesight, and it shows how fog itself was burned away using fire. It is also the story of human endurance, exhaustion, and decision-making under extreme pressure. Before the Second World War, aviation was largely a daytime activity. Most aircraft were designed, tested, and flown with sunlight in mind. Night flying was possible, but night landing was crude, risky, and unforgiving. RAF airfields relied on oil lamps placed along the runways. Paraffin flares were used to mark landing areas, and sometimes vehicles lined up with the headlights switched on. Pilots judged height using instinct rather than instruments. Distance was estimated through experience rather than measurement, alignment depending on scattered points of light that could easily be misread. There was no standardised glide path, and there was no electronic landing guidance in the early days. In poor weather or darkness, pilots were forced to guess, and guessing cost lives. As Bomber Command moved to night operations to avoid German fighters, losses near home airfields increased sharply. Many aircraft survived enemy action only to crash within sight of safety. Crews were exhausted, airfields are crowded, and weather is unpredictable and often unforgiving. Courage alone was no longer enough, and precision became essential. Early RAF solutions focused on procedures rather than technology. Airfields developed funnel-shaped lighting systems to guide aircraft inward. Landing circuits were widened to reduce the risk of collision, and strict patterns were introduced to bring order to returning traffic. Pilots flew standard heights and timed turns carefully. Altimeters were set to QFE, so height above ground could be read directly. In theory, this provided accuracy, but in practice errors crept in. Small pressure differences mattered, navigation inaccuracies mattered, fatigue mattered most of all. Crews returning in the early hours of the morning, after hours of tension and stress, struggled to fly perfect patterns and to focus on their instruments. Human limitations became increasingly obvious. Vision deteriorated in darkness, judgment faltered under fatigue, memory and attention failed when overloaded. The limits of the human brain were being exposed, and technology would have to compensate. The central problem was visibility. Darkness removed external visual references. Fog removed everything else. Even a skilled and experienced pilot cannot accurately judge height or alignment without a visible horizon. Spatial disorientation caused pilots to misjudge attitude, and visual illusions led to overcorrection or delayed responses. Controlled flight into terrain became a frequent cause of accidents, and the RAF accepted a critical truth. The human brain is unreliable when exhausted and deprived of visual information. Any effective landing system had to function independently of sight. Aircraft needed to be guided by something more reliable than human perception. Radio waves provided that solution. The beam approach was not a modern instrument landing system, but for its time it was revolutionary, and it does lead into the story of the ILS, used in modern-day aviation. Directional radio transmitters were positioned beyond the runway threshold. Two overlapping beams were broadcast. One beam was offset slightly to the left of the runway centerline, and the other was offset slightly to the right. Each beam transmitted a distinct audio signal. Dots are transmitted on one side and dashes the other. The pilot listened to these signals through his headphones. Hearing dots meant the aircraft was to the left of centerline, hearing dashes meant he was to the right. When the two signals merged, they produced a steady, continuous tone, and the aircraft was perfectly aligned. The pilot flew the sound rather than the view. There were no external visual references, and there was no room for instinctive correction. Vertical guidance came from a second set of radio beams. One signal indicated the aircraft was too high, and the other indicated it was too low. But before this system came into use, it was purely done based on time outbound versus airspeed and an altitude at a certain time. The pilot balanced both dimensions at once: lateral alignment by audio tone, vertical profile by audio tone. It demanded precision and absolute concentration, and was very difficult after a fatiguing long mission. Flying the beam approach was mentally exhausting. Pilots had to suppress natural instincts, they had to ignore bodily sensations, and they had to trust the radio signals completely. Any distraction could break concentration, and radio interference affected clarity. Engine noise masked signals, and crew conversations had to be carefully controlled. The captain flew the aircraft manually, and the flight engineer monitored the instruments closely. The navigator confirmed timing and position, and the radio operator kept the beam tuned in to the pilot's headsets. Crew coordination became critical. This is the beginning of what we now call in modern aviation crew resource management, how a crew interacts together. These approaches are flown entirely by hand. There was no automation, and there was no flight director guidance. Small errors could escalate rapidly, but when flown correctly, the system was remarkably effective. Accident rates declined and recovery rates improved. The beam approach saved aircraft and saved lives. The beam could guide aircraft accurately downward, but it could not remove the fog. Pilots still needed visual reference during the final moments before touchdown, and in British weather conditions, dense fog often formed close to the ground. An aircraft could fly a perfect approach and still see absolutely nothing. Fuel became a deciding factor. 2 or 3 approaches, it's time to go somewhere else. Diverting meant additional flight time. Additional flight time meant running out of fuel. Crews faced impossible choices: attempting to land without visual contact, divert and hope for fuel lasted, or abandon the aircraft ultimately. Technology had solved most of the problem. Nature blocked the final step. The response was somewhat unprecedented. Here we introduce FIDO, Fog Investigation and Dispersal Operation. The concept was simple and extreme. Heat the air, remove the fog. Fuel pipelines were installed along both sides of the selected runways. Hundreds of burners sprayed petrol into the controlled open flames. When ignited, walls of fire rose beside the runway, air temperature increased rapidly, and the fog evaporated. A clear landing corridor emerged. Pilots described the experience as landing in an inferno. Heat buffeted the aircraft violently, turbulence disrupted the pilot's control inputs, and the engines inhaled hot, thin air, making them less efficient. But the runway was visible. FIDO consumed enormous quantities of fuel, around about 100,000 gallons per hour. It was expensive, it was dangerous, and it was only used in emergencies, but it worked. Entire squadrons were saved. Technology reduced risk, but humans still had to operate it. Bomber crews were exhausted: long missions, cold cockpits, constant noise, continuous fear. Cognitive performance degraded steadily, and reaction time slowed. Memory became unreliable, tunnel vision narrowed attention. Beam approaches required intense focus at the worst possible moment. Some pilots fixated on the audio cues, others over-controlled the aircraft. Stress caused mistakes even with excellent equipment, and the RAF began to understand human limitations. Crew coordination improved, and clear call-outs were encouraged. Standard procedures were reinforced. The foundations of modern crew resource management were quietly being laid. RAF night landing was a battle between science, darkness, weather, and human limitation. The beam approach taught pilots to trust sound over sight. FIDO demonstrated that the environment could be altered. Together, these innovations have transformed aviation safety. Modern instrument landings owe their existence to these wartime solutions. Every safe landing in zero visibility today carries the legacy of those who first learned how to overcome the darkness on their arrival back at home. Today we benefit from the instrument landing system and aeroplanes that are capable of landing themselves in what we call Category 3 landings, automatic landings from the aircraft and autopilot. We no longer need to see the runway to be able to land the big jets. The limitations faced by bomber command during World War II progressed aviation science rapidly through necessity. Through having to operate in the hours of darkness to avoid the losses suffered in daylight raids, the RAF had to turn to science to overcome the elements. Radio waves were new, and they were developed very quickly. We have an awful lot to thank the RAF and the scientists for in modern aviation, bringing on crew resource management, bringing on the instrument approaches we have, and engine and aircraft technology. The war was not just about dropping bombs, but also about science and how to advance faster than the enemy. Lest we forget.